Well, thanks so much for coming to hear me again. I continue to be surprised that you're back, but anyway, I'm very happy you're back. Let's see. Yes, it works. So that was the plan, and I think we are following this plan pretty well. So just to remind you, in our first session, we talked about parity violation in atoms and molecules and how that works. And then yesterday we had yesterday we had two sessions, and they were devoted to ultralight bosonic dark matter. And we talked about NMR searches, atomic clock searches, about sensor networks, about fast oscillation of fundamental constants, and the RESL experiment, which stands for Weekend Relaxion Search Laboratory. We talked about how to look for dark matter elephants in the Earth with a network of gravimeters. And then we discussed this intriguing and completely different framework for what dark matter could be, namely the axion quark nuggets. And finally, we briefly discussed the first, or maybe one of the first, I don't know, depending on how you think about it, dark matter search with antimatter, which brings out these questions about how can we think about asymmetric interactions of dark matter with matter and antimatter. It's very interesting, bringing two big problems together, so to say. So today, what I would like to do is I would like to maybe go back at first, and I talked to some of you who are theory students, and some of you said that you hardly ever have any contacts with experimentalists. So I thought I'm going to give you a little bit of brief introduction to one particular weird kind of experiments. These are nuclear magnetic resonance experiments at zero and ultra low field. And maybe you remember last year we used some of these to look for very low frequency dark matter. So that's the relation there. After that, I'd like to say a few words about indirect searches. We also briefly discussed them yesterday, but maybe I'd like to show you a couple of slides on that. And finally, the last thing that I'd like to do today is I'd like to introduce a new interesting tool for all kinds of interesting physics, and I will try to sort of sketch what kind of interesting physics can be done with this. And this is Gamma Factory, which actually is based on LHC, but LHC that's not going to be used as a collider but as a light source. So we'll get to that soon. Yeah, I stole my own slides from another meeting for this. I meant to change this, but I forgot. So this is not an abstract painting, actually. Eventually, in a few minutes, you will see that this is a very, very informative picture that tells you about the experimental setup, about the experimental procedure and the results. And yeah, if you don't believe me, let me just show you now. This is an atomic magnetometer that consists of a vapor cell, and there are two laser beams that intersected. One is so-called pump beam, another is called the probe beam. And this is a molecule we are studying, and this is a parahydrogen molecule that attaches to this more complex molecule, and this line shows the experimental spectrum. So you see, it's like a full disclosure of what is going to come, but looks like an abstract painting. Anyway, yesterday we briefly discussed that zero field nuclear magnetic resonance is actually something that's quite unusual in the field of magnetic resonance, at least until recently. And the reason for this can be understood if you think about the nuclear magnetic resonance experiment as something that happens in three stages. So at first you need to produce somehow polarized nuclei. That's the first thing that you do in an NMR experiment. Now you are of course doing it for fun, but you also want to do something useful with this eventually. And there are two sort of big direction in nuclear magnetic resonance. One is called imaging. So in imaging, you want to know where the nuclear spins are. For example, in your body. Okay, that gives you spatial information. And then there is another modality in NMR, is where you actually do not care where things are, and typically they are in an NMR tube. So you put some chemical in it, and you want to know what is it. And this is the goal of spectroscopy. So through the measurement of NMR spectra, to say what kind of substance you have. And so so in the second stage of NMR, either it's imaging or spectroscopy, you are somehow encoding the useful information into the spins somehow. I will give you examples. Typically in the angle of rotation of the spins in the magnetic field. And then the third and final stage of the NMR experiment is you need to read out that information that you just encoded, and that's called detection. Actually, these are sort of the three stages of NMR, but it turns out that many experiments can be also split into these kind of three stages. For instance, atomic magnetometry. You prepare polarized spins, you let them evolve in the magnetic field, and you read them out. Or electric dipole moment searches. You prepare polarized spins, you let them precess in the electric field now, and then you read them out. So it's a pretty general thing. Anyway, back to NMR. The classic nuclear magnetic resonance uses magnetic field in all of these three stages. So, for instance, for polarization, what you do is you just put your nuclear spin system in a magnetic field, and you let it equilibrate, and there is an excess of polarization in one direction versus the opposite direction. That's called thermal polarization. In the encoding stage, if you are doing imaging, you apply strong magnetic field gradients, so your polarized spin evolve differently in different parts of the system, and then you read that back, and you know where your spins are. And in spectroscopy, you're typically relying on the effect that's called chemical shift. Chemical shift is a slight diamagnetic screening of the external field that depends on the chemical environment. Okay, and for different chemical environment, your NMR lines are shifted differently, and if you take this spectrum, you can say what kind of environment you had. And finally, the detection in an NMR experiment typically uses Faraday induction. The way it works, you have a pickup coil, and you have nuclear spins, and they precess in the magnetic field, and this changes the flux, magnetic flux through this coil, and there is induced voltage, EMF, and it's proportional, if you remember your electrodynamics, to d phi dt, where phi is the magnetic flux, and it's a time derivative of the magnetic flux. Okay, but if I have a certain number of spins, there is some total magnetic flux, and then they precess, and the time derivative is proportional to the frequency of the precession, and that's proportional to magnetic field. So a classic NMR experiment picks up 1 power of magnetic field in the signal that you detect that comes from polarization. The higher the magnetic field, the higher the nuclear polarization, and 1 power from detection. So typically NMR people are used to their signal scaling as approximately like b squared. So if you come to them and they say, I want to do NMR at zero field, they would normally say you're nuts, because your signal is going to be very small, and you also need magnetic fields for detection, for encoding. So there are 3 reasons why you need magnetic field, and you want to work without magnetic field. But I wouldn't be telling you about this if it wasn't possible, and the idea is that you find clever ways to eliminate the need for magnetic field in all of these 3 stages. So for example, on the first stage of polarization, so normally it's thermal equilibrium, but what you can do is, for example, you can, I already mentioned this yesterday, you can do spin exchange optical pumping, where you take, for instance, an alkali atom, of say rubidium or cesium, and you shine polarized laser light on it, and it's very easy to transfer the light polarization into atomic polarization. Basically, every absorption act transfers the angular momentum from light to the atoms, and then you let your alkali atoms collide with whatever system you are trying to polarize. For instance, xenon 129 for the Casper wind experiment. This way you transfer sort of this light polarization onto atoms, and this process doesn't require any magnetic field. And I'll tell you about a couple of other interesting tricks how you can do polarization not relying on magnetic field. So we got a way with 1 power of magnetic field. My my favorite technique for polarizing nuclei, and in fact I must confess it's my favorite technique for doing everything, which is do nothing, okay, and just let it happen by itself. It was wonderful. So you say you have an ensemble of n spins, and you just randomly throw them like dice. So some of them are up, some of them are down, and on average you would have 0 polarization. But there is a square root of n excess. We don't know whether we will have more of the spins up or more of the spins down, but there will be some excess. And if n is equal to 1, there is a wonderful mathematical property, you know, that square root of 1 is equal to 1. So if you're talking about very small number of spins, your what's called stochastic polarization is just as big as the highest polarization you can obtain if you work very hard. So why work hard? And you might say this is crazy, because how can you do NMR with 1 spin? But in fact, this is reality. There are several groups, including here in Israel, in the Weizmann Institute, who work with a small number of spins, and this is becoming quite popular. And in order to do this, you need to find techniques sort of to do magnetometry on an atomic scale, and this is possible with something that's called nitrogen vacancy color centers in diamond. It's a separate story. So, but just to let you know, this is not science fiction at all. Yeah.
So how small is n? How many atoms?
1. Could be 1. Really 1. Could be really 1. So now people do a spectroscopy of so 1 molecule with 1 spin sensor, and it works like this very, very beautifully. All right. So there is another very, very cute technique for making high nuclear polarization, and it has fundamental physics in it. So I'm very eager to tell you how this works. And this was actually introduced by these two guys, Cliff Bowers and his advisor Daniel Wittekamp in 1980s. So it's relatively fresh, and now a lot of people in NMR use this technique. It's called FIP, parahydrogen induced polarization. And since you may have forgotten how molecular hydrogen works, I'm going to give you a short course. This is called Parahydrogen 101. Okay? So in Parahydrogen 101, you go to Wikipedia and you find this picture, and you find out that the hydrogen molecule consists of 2 green hydrogen. No, it consists of 2 hydrogen atoms, and the ground electronic state of this molecule is a singlet state. singlet electronic state, but each of these hydrogen has a proton as a nucleus, and the proton has a spin 1/2. So in principle, you can have two types of the total ground state spin. Two spin 1/2s can add, if you would remember, into 0 or 1. And if these guys are in a singlet state, that is called parahydrogen, and if they are in the triplet state, it's called orthohydrogen. So that was parahydrogen 101. Any questions on this course? If there are no questions, we can almost move on to the next one, except it's one very important thing that I would like to already mention here. So now, so if you have this molecule, okay, you can think that you have one hydrogen, which is a boson, and another hydrogen atom, which is a boson. And so the overall wave function of this system, no matter what, has to be symmetric with respect to the permutation of two hydrogens. And if we write the molecular wave function, then it's electronic wave function, right? And we said it's a singlet, so it's anti-symmetric. It's then times vibrational. It's always symmetric times rotational, times nuclear spin wave function. So this is the total wave function that we can factorize like this. And so for the overall thing to have positive symmetry, you can see that the nuclear spin symmetry dictates the symmetry of the rotational state. If you recall, for rotational states, the parity, the exchange symmetry is -1 to the power of j. And this has a very, very interesting effect. So you can forget about the energy difference. Actually is very small, even parametrically, but then averaged over the molecular wave function, there is no energy difference here, and yet the spin nuclear spin symmetry selects what is an allowed rotational state. And a rotational state has a pretty high energy. Let me show you on the other slide here. And now you notice we graduated from parahydrogen 101 to parahydrogen 102. So if we look at the two lowest rotational states in the parahydrogen molecules, we can look at the difference of their energy. This corresponds to 175 Kelvin. Okay, so this is a relatively big energy difference, and it's dictated again by the nuclear spin symmetry that itself doesn't have any energy in it. And so what it means is if you take hydrogen gas and you just cool it and let it equilibrate, then if you already at the liquid nitrogen temperature of 77 Kelvin, you have about 50% polarization into this para state, into the singlet state. And if you go down, for instance, to 4 Kelvin, the liquid helium temperature, you basically have 100% of molecules being in the para hydrogen state. So you create some sort of a nuclear spin order just by cooling it. It turns out that the relaxation times here are very long, and if you just cool it and do nothing, then it will take a couple of weeks typically for hydrogen to convert to the para form. But what you can do is you can add what scientifically is called a catalyst, and what it is really is rust, iron rust. It's you put some of it in the container, and it has very strong gradients, and this accelerates this conversion process, then you can do it essentially instantaneously, and then it's very easy, basically by cooling, to produce highly ordered spin system. And again, this is a singlet state. So what this is here is you would notice spin statistics, both statistics in action. Okay, that's very beautiful, I find. Anyway, what you can do then is you can have a reaction of this para-hydrogen. So I should notice the following, that para-hydrogen is a singlet state, so it doesn't have any magnetic moment associated with it. So you cannot do an NMR of para-hydrogen itself. But what you can do is you can do a chemical reaction. It's called hydrogenation reaction, when the hydrogen attaches somewhere, and this creates sort of non-equilibrium distribution of your spin states and makes your signals observable. And in fact, this is a way to produce very high polarizations. I'm not going to go over this elementary quantum mechanics example, how this works. So now maybe I have convinced you that there are good ways to polarize nuclei without the magnetic field, so laser polarization or para-hydrogen polarization. And let me now tell you how we get rid of the need for magnetic field in the encoding stage, and I'm going to use the example of spectroscopy. So as I already mentioned, typically NMR spectroscopy is done by measuring differences in the chemical shift. And one thing that I like to mention to you about this chemical shift, that there is a sort of traditional unit for it. It's called ppm, parts per million. And if you have a particularly strong chemical shift, it's sometimes a few hundred ppm or something like this. It's a relatively tiny shift. Okay. So we are going to use something else, and what it is called a scalar coupling or J coupling, and it was discovered in the early 50s by Erwin Hahn and Charlie Schlichter's group independently. And in order to understand what this is, imagine that you have a molecule, and on this molecule you have two nuclear spins. Each of these nuclear spins has an associated magnetic moment, and you can just write down what is the interaction, dipole-dipole interaction between these two magnetic moments. And you know the dipole formula, so you write spin 1 times spin 2 divided by the distance cube, and then there is this pesky geometric factor, 1 minus 3 cosine square theta. So now suppose that what you do is you have this molecule, and it's usually in a gas or in a liquid form, and so these are your nuclear spins, and then your molecule is allowed to tumble around. What this leads to is that this geometric factor, so if you have two spins with a fixed direction and you sort of average over their relative orientation, the dipole term goes away. So mathematically, I guess it's a property of Legendre polynomials. And so people thought that once you allow this tumbling, so meaning you're working with a gas or a liquid, then the dipole interactions will average. And so what these guys have discovered is that it doesn't fully average. So there is a residual coupling that remains. It doesn't have this factor, so they call it scalar coupling, and it's just I1 times I2. And in modern language, we understand this effect as the second order hyperfine interaction. So basically what happens, you have one nucleus, here, and it perturbs the molecular wave function. And molecular wave function sort of is a global thing, so it carries the information about this perturbation over the whole size of the molecule, and then you have the hyperfine interaction again on the second side, and this way these two spins talk to each other. And typically this is a very small energy in units of frequencies. This corresponds typically to something like 100 hertz or so. And so if you are doing normal NMR experiment, this is the tiniest term in your Hamiltonian. So so now if you buy yeah, what is? No, one molecule, two nuclear spins on one molecule. Yeah.
Okay, but each molecule can interact with its environment, right?
Yeah.
How we can throw away this background? How we know that it does not destroy the...
Well, it causes the background and stuff causes relaxation eventually, but we're talking now about interactions within the molecules, and we will find experimentally that the relaxation doesn't wash this out. It's much slower. So we see, yeah. So just to give you some idea, if you buy a high field NMR machine, and high field these days means up to about 20 Tesla or something, and you use protons as your spins, you are talking about something like a gigahertz NMR frequencies, gigahertz, and this is 100 hertz. So it's a very, very small perturbation typically. But if we go to zero field, then every other interaction will be zero, and this one survives, and this becomes the dominant and the highest interaction. So we it's a real revolution when we turn everything upside down, which was the smallest is now the biggest. Okay, so now we have figured out how to not use magnetic field here on the polarization stage and encoding stage, and in the detection stage, we instead of Faraday induction, we use an atomic magnetometer, a diamond-based magnetometer, or a superconducting magnetometer called SQUID, and those don't care about the frequency. They work very well with low frequency fields, and so we don't need a magnetic field here either. And so this NMR experiment, okay, again, typical NMR experiment, you have this high field expansive magnet, and our experiment is very, very different. So instead of a magnet, we actually need to bring a magnetic shield, because we don't want, even the Earth field is way, way too large for what we need. So we bring a shield, and here's our atomic magnetometer that I already told you about. It's in the middle of the shield, and we still have an NMR tube, okay, and it's we put it inside the shield. And so, for example, if we use the parahydrogen polarization, then we do the following thing. It's kind of fun. You know, you bring parahydrogen in a little straw, like Coca-Cola straw, okay, and so you bubble it, so you have this chemical reaction that is going on, and then you observe. So so there's this is the pulse sequence, as NMR people like to say. So you bubble for a few seconds, and then well, it turns out that after you have reacted your parahydrogen with the molecule you want to study, you need to do one more thing to get observable signal. You need to give it a small pulse of a magnetic field, but it's really a very easy pulse. It's a small field for a short time. That's not a problem. And then you just look at the signal from your magnetometer, and you get this spectrum. And okay, you say, well, I'm showing you some theoretical pictures or something, but let me tell you the real experiment, about the real experiment. So what we've done, this is a molecule, this is a complicated thing with aromatic ring, and this sort of an additional group here. It's called styrene. So there is a double bond here. And if a parahydrogen molecule comes onto it, it can attach here and break this double bond. And so now you have two of the parahydrogen, two hydrogens of the parahydrogen molecule sitting on there. And then here is the molecule. So we distinguish these are carbons in different chemical groups, and then we see the spectrum in our experiment. This is the actual experimental spectrum, and it looks actually like a big mess. But then you start looking at it a little bit more closely, and you actually can discern that, for instance, so these are these hydrogens, and this is this carbon, and you find that this group produces two groups of sharp lines here and there, and this group produces lines that are so more perturbed in here, and the red ones produces one group of lines here, and in fact you will see that I'll show you an example that we can understand the entire spectrum. So now you can see that this is actually the whole experiment. So this is styrene, this is parahydrogen again, and this is the spectrum. So now you can do start doing useful things. For example, you can do spectroscopy of different compounds, and when a physicist looks at these molecules, they basically look the same. It's a ring with something else attached to it, and for chemists, these are very, very different beasts, okay? And in fact, their J-coupling spectra are completely different. And this illustrates the fact that you change the molecule very little, for instance, add the oxygen atom, and now you have a completely different spectrum. It's 100% different. So in the ppm units, if you want, this is a million ppm, as opposed to maybe 100 ppm or something. And the other thing that I want to show you is they are the same spectra in detail. And let's just zoom at this spectrum over here. So at first, if you look at this, you must say, oh, you guys have to work on your signal to noise, and your apparatus produces some garbage. You never understand this. Well, let's zoom it further, and what you see here is actually the experimental result, and this is the density matrix simulation, and you can see that we can reproduce everything. So it's not actually garbage; it's an informative signal that tells you about the details of molecular structure. And you can also zoom even further on one of the lines, and you see that these are exceptionally sharp lines with the widths of a few millihertz over here, which is unheard of or at least maybe not unheard of, but very, very hard to get in conventional NMR. Anyway, so this is an interesting platform, and then you ask yourself, now I have this new thing, what can you do with this? And in addition to chemical analysis, for example, and one of the things that we did together with a group of colleagues, and this was initiated by Professor Xinhua Peng. She is a faculty member at the University of Science and Technology at Hefei, and then eventually was done in our laboratory at Mainz by these folks. You have heard about NMR quantum computing efforts, and this is a zero field NMR. It's very different from regular NMR, so we wanted to see if we can do quantum gates with this, and the answer is yes. And it's quite different and has some advantages and disadvantages. compared to high field quantum computing, but it's a sort of a new platform, and certainly has capabilities that high field NMR doesn't afford. But I don't want to talk about it here. And of course, just to remind you, I already showed you this slide, that then we figured out how to use this for dark matter search, with the ideas being that dark matter could be this background classical field, not screened by shielding, oscillating at the Compton frequency of the underlying particle, and being a relatively narrow line, because the oscillation frequency is given by the total energy of the particle, and most of it is its rest energy and a little bit of kinetic energy due to the motion in the galaxy that cannot be faster than the escape velocity, and that gives this sharpness for the line. And this, so it's a Casper wind experiment specifically, and I already showed you these results that we were happy to produce last year. All right, so that was, before I show you the picture of this gentleman in the front row, so that was a little taste of what zero field NMR is, and I would like to maybe pause here for a second and take questions if there are any. Yes?
So I'm not sure exactly I understood how the J coupling encodes the spins. Can you maybe elaborate? What exactly does it, I mean, the encoding sort of prepares them to be measured, right? Or makes them rotate to be measured? I'm not exactly sure how.
So the frequencies of the so now you have the spin interaction, so you now can add these spins into different total spins, and the energy differences they depend on the molecule and are generally 100% different from one molecule to another. So you just measure that spectrum, you see how many lines you have, that tells you about the multiplets, and then the sizes of the couplings also tell you what kind of molecules those are.
It's sort of like a beta S, but I mean, they oscillate around these two energy levels, and then you measure that. Okay.
Yeah, that's right. Any other questions about this? Pavel?
Is there something that Zool can see that normal NMR cannot?
In what respect? In terms of?
Like a detection of some coupling, or like we can see. Can we see J coupling with NMR?
Yes, we can see generally J coupling with NMR, but not all of it. So I told you about the simplest type of J coupling, which is just a scalar. It's one parameter J that multiplies I1 dot I2. In fact, symmetry allows it to be a tensor. And in high field NMR, there is this phenomenon called truncation, because you have a large magnetic field. Okay, so anything magnetic just turns around it very quickly, and you basically average everything except the projections along this field. That's called the truncation. We don't have a truncation here, and so we can, in fact, see these tensors. And if you remember our first session, I mentioned that there is one way to measure molecular parity violation, and it's based exactly on this. So this is one example. Okay, good. So the second thing that I wanted to mention to you is a little bit about exotic potential and indirect searches for exotic particles. So the idea, as we discussed, goes back to a paper by Moody and Frank Wilczek from 1984, that they basically said, well, if there is some, let's say, a scalar mediator or vector mediator, what kind of extra forces can appear between, say, two scalar particles or two particles with a spin, and they may sort of had a few examples of this. And then this idea was extended some years later by Bresco and Moschow, and they published a sort of a catalog of these interactions. Basically, a lot of people looking for these exotic spin-spin interactions, for instance, Roy, Ozeri at the Weizmann Institute, they used these. But there were a few issues, some minor, some more serious, various signs inconsistencies, and some missing terms, and so on. And so that motivated sort of a fresh look, and this was done a couple of years ago with Pavel Fadeev here being the lead person on this. And there are a couple of papers. There's a Physical Review A with this new and improved catalog, and then some addition to this that's on the archive and possibly is going to be published later on. And this is, by the way, one of the brilliant scientists in our group, Lykurgas Buchas, looking at Pavel's.
One example, may I say, people that are in the audience are looking for these potentials, right? So in Dobresko and the other author,
Moschow, yeah.
Yes, so we sent them an email after we published saying that they have a sign error in the tensor interaction, which is a third of the possible interaction. And we also told them where exactly, and they said, okay, we will check, and they did not come back to us. So
They're still checking.
or they just said we are right, or they understood we are right,
Yeah.
and that's it. But yeah.
Okay. Anyway, so this can be this stuff. In fact, was motivated by this work, which is again an example of the couch. I introduced this concept, Gilad. You weren't here, of the couch physics. Maybe you know where you don't actually do serious theory. You don't do the experiment. You use somebody else's data and theoretical results, and then you get something out of it. And something means a Physical Review A or something. But anyway, so this particular work here was actually motivated by the work that Roy Ozeri has done, measuring precisely the forces between trapped ions, and he collaborated with my former student Derek Kimball, and then they have extracted some best, actually at that time, limits on exotic electron interactions from Roy's experiment. But it seemed a little weird to me that sophisticated experiments with ions could do better than just normal high precision atomic spectroscopy. And so I was very lucky to get this gentleman who then was an undergraduate student. His name is Philip Ficek. He's currently some very sophisticated quantum gravity something theory graduate student in Krakow. But at that time he was just an undergraduate, and I asked him to look at the data and theory for helium. It's a relatively simple 2-electron atom, and there is super precise data that are available in the literature, and Krzysztof Pakucki is the master of calculation of simple atoms, and together with his St. Petersburg collaborator Yerochin, they have done very high precision calculations of the line positions in helium. And so what Philip did as his summer assignment, I asked him to take a beautiful book by Bethe and Salpeter called Quantum Mechanics of 1 and 2 electron atoms, I believe it's called, and take the Dobreska-Moschow potentials and calculate the matrix elements with the known wave functions, really undergraduate stuff, and then compare with the differences or lack thereof between theory and experiment. And this has resulted in, so these are some of those potentials, and this has resulted on some limits on exotic couplings that in fact improved significantly on what Derek and Roy had before from ion spectroscopy. So that was very nice. These were the Bresco-Moshev potentials, and here is Pavel's potentials that now have to replace them. Okay, so anyhow, and then we were sort of inspired by the success of this approach with helium, and I learned from a talk by Masaki Hori from.
Can I ask something? But if you look at this, you mentioned axion there or some exotic atom. But if you look at this as a way to constrain the parameter space indeed of pseudoscalar or even axial vector models or something, then this will never compete with the other bounds, right? Is it true?
What do you mean? Some of the bounds are best from this.
Really?
Yeah.
But if you have but if you have something like ALP, which couples to matter, they are better.
Yeah. Well.
Axial vector, I mean, modulo the anomaly.
You have to see exactly what you are comparing. So this was, for instance, electron interaction, and sometimes it's semi-leptonic, and you have to make sure you are comparing the same thing. So oftentimes this gives different combinations of constants, but for certain combinations, I'm pretty certain this gives the best.
I think maybe as physics have this perspective. I think for electrons, the bounds from the long-range spin-dependent interaction are not so good. Not really natural.
Yeah, and the range here is determined sort of by the atomic size. So the cutoff is when the mass of the carrier calculated in the Compton length becomes comparable to the atom, and so this sort of relatively short.
You're saying that there's maybe a sweet spot where you cannot compete with other axions, because if you couple to the electron, you can do a loop, and then you couple also to electromagnetic field, and then you have other constraints much stronger.
Maybe.
So unless you are finely tuning your theories, then you cannot avoid one.
That
or the other. So if you can take honest to God like axion theory, I think you will never, unless there's a sweet spot where the other are suppressed, you are never really probing new regions. That was always my feeling about those walls. Which doesn't mean that you shouldn't measure this and all this, but to match it to a relatively simple theory like axion exchange.
I see. Yeah, well, it's a
So the several potentials drawn over there, the second one is the one that you constrain here?
it's a 3-3. So that was published before Pavel's catalog. So these are the Bresco-Moshev. So this one is this potential.
You can match it to the coupling constants just by looking at the structure.
Yeah, that's why I think the next one comes like the baby, like the.
All right, but thank you, Gilad. Yeah. But we were quite inspired actually by the success of the helium enterprise, and then I learned from the talk by Masaki Hori about these beautiful experiments with antiprotonic helium. And as I described, what happens here is you have an atom that has a helium nucleus. It has one electron in the ground state, and then you add an antiproton, and there is if you excite sort of relatively high excitation with about principal quantum number of something like 30 or 40, it's a heavier particle than electron, so it's a smaller Bohr radius, but the Bohr radius for Rydberg goes like n squared, and so if when you get to 30 or 40, you see that the size of the wave function for the antiproton and electron are relatively similar, and so you get this beautiful atom like this, and you can now do a calculation, and the calculation has been done by Dr. Korobov, and the experiment by Masaki Hori and colleagues. And again, we use the same couch streak, okay, and it's a little bit more difficult because the wave functions are not really in a nice form that Beta and Salpeter have in their book, which are just analytical. But nevertheless, in this case, Philip and Pavel joined forces on this and published this set of constraints on exotic potential. And this was, we were super excited because this is now semi-leptonic interactions of antiprotons. So these are the constraints involving antimatter. So there are a lot of firsts. It's the first antimatter semi-leptonic constraint and the first velocity-dependent constraint and whatnot. You know, so it's pretty interesting, I think.
Why semi-leptonic?
Because it's antiproton and electron.
Ah, okay. What was the matter of the proton helium plus system was like a Rydberg atom, and then the electron?
So this is so it's a helium nucleus, an electron in the ground state, and the antiproton in an excited state.
What is the lifetime of this?
Some microseconds. It's relatively long. Yeah, and actually this there's some sweet spot, for this particular. Because of they're long-lived for this particular combination of quantum numbers. That's why the precision spectroscopy is available. It's really beautiful. Yeah. Interestingly, if you are doing this kind of thing, you don't really need it to know experimental details because you can just read things from the numbers from the papers. But it's beautiful. Okay. Here's the first, right? We were very proud, so we put this in the paper, and people haven't complained about these statements. Okay, and then I also talked a little bit yesterday about direct searches for antimatter, for dark matter with antimatter using the trapped antiprotons in the base experiment. So we published the first. You weren't there. We published the first results together with base on these. So if you there are things to compare this with. You can derive some astrophysical constraints on what it could be, and the experiment beats them by many orders of magnitude. If you assume symmetry between interaction of dark matter with matter and antimatter, this experiment is not super impressive, but it probes directly possible asymmetric interactions. So it's now very interesting to see what it means theoretically. Okay, any questions on that before we go to the final topic? How much time? I have like half an hour, right, Eric? Good.
Can I ask one more thing about the previous thing? So how much this is less precise than the analogous sound that you get from matter?
Well, here it's for helium it was electron, and here is electron antiproton. So it's technically different couplings.
But probably there's also bound on electron proton, which is hydrogen.
Yeah.
So which is much better, or is it?
That
even if you do cross measurement of that, it's almost the same precision.
I don't remember specifically, but I think, for instance, I have to look, or we can ask Pasha to look.
If you assume that the coupling to proton is the same as the coupling to antiproton, then I believe the bounds are similar.
Really?
Is this your question?
Yeah.
I believe it. keep the similar. But we didn't compare it because it might be different, so we didn't compare it to this in the paper.
Okay, we are switching gears in a dramatic way now, and I'd like to tell you about this gamma factory business at CERN. And this is a picture of Galileo Galilei. But it turns out that this looks almost identical to the picture of the person who is the main proponent of this idea is Professor Viti Krasny, and he looks just like Galileo. So it's really funny when I go to Gamma Factory meetings, show this picture. Anyway, I'll tell you why I think this is very exciting. So maybe we use already this picture here. So suppose you have some storage ring, and let me go this way, and you have your ions circulating in a storage ring. Specifically, we are talking about LHC or SPS. SPS stands for something superconducting proton synchrotron, something like this. It's currently used as an injector to LHC. And the idea is that normally these things operate with some kind of either protons or bare ions, for example lead, just the lead nucleus without any electrons. But it is also possible, and I will show you later that it has been done, to put sort of what's called a PSI, partially stripped ion. For instance, a lead nucleus and one electron, so hydrogen-like lead, for instance. So you can put this thing and circulate it in the orbit. So now you can take a laser, like this, for example, and you can shine the laser towards incoming ion, face on. And then there are a few interesting things that happen. So these machines have highly relativistic ions in them. Okay, so we need to remember our special relativity. And what special relativity tells us is that if I have some energy of a photon from a laser, and this is typically 2 electron volts. This is 2 electron volts, for example. Then if I go to the frame of the ion, it's up shifted by a factor of 2 gamma, where gamma is the relativistic factor of the ion. So it's a much higher energy photon as seen by the ion. And so what you do here is you can choose the energy of your laser, or you can choose the gamma factor, the energy of the ion, and you can match an atomic resonance with the frequency of the laser. And so here you can see already one interesting thing, that you take a normal laser and you can boost it. So the gamma factor is 3000 typically for LHC, and you can take a couple of electron volts and multiply by 6000, so now you are in the tens of kilovolt or something. So you can now do X-ray spectroscopy basically of things using normal lasers. So it's already interesting. But then there is another thing that happens, and maybe I will go to the next slide to show you. So you can see what is happening either in laboratory reference frame or in the frame of an ion. Let's first go to the frame of an ion. So in the frame of an ion, I have this stationary ion, and then a photon is coming in. And remember, this is now boosted by a factor of 2 gamma, right? So it's a highly energetic photon as well. Then this photon excites the ion to the excited state, and then the ion relaxes back by emitting a photon, and in general it's emitted in an arbitrary direction. Yeah. So now we can see. So that's what happens in the ion frame. A photon with the same energy emitted in the arbitrary direction. So now we can look at this secondary photon in the laboratory frame. And in the laboratory frame, there are two pieces of magic that happen. First of all, due to relativistic transformations, whatever direction where this ion is emitted, in the lab frame, it's all in a narrow cone of 1 over gamma in the forward direction. So towards the laser. And the second thing that happens is you have to do your Lorentz transformation of energy again, and there's another factor of 2 gamma. So now you have a photon shining back at the source with an energy 4 gamma squared times the initial energy. So with this we can go to energies at the LHC up to, say, 400 mega electron volts. So very high energies. And one very important thing that I need to tell you that makes this important. There are sources. These sources are called, I think, inverse Compton scattering light sources, where you have an electron ring and you do the backscattering from free electrons, and it also produces photons of similarly high energy. But here, you are not scattering on a free electron. You are actually scattering on a resonant atomic system, and that boosts the cross section enormously. The cross section on resonance is on the order of the square of the wavelengths, and so this is huge cross section. And the bottom line is you can have now a light source with tunable energy up to very high values, up to 400 MeV, and with fluxes that exceed the current fluxes of other sources by maybe 8 to 10 orders of magnitude. That's really a big boost. You may say, okay, this sounds sweet, but maybe the ions won't survive in a ring. Okay, maybe they somehow will get ionized immediately while going through turning magnets of the accelerator or something like this. And you can make some predictions. And actually, I'll tell you some history. We looked at this many 20 years, 25 years ago, and we predicted that it should be possible. But just last year, or I guess maybe already more than 1 year ago, this was demonstrated, in fact, at CERN. So helium-like lead and hydrogen-like lead was injected into the SPS and circulated for maybe 10 minutes or something. And then hydrogen-like lead was transferred from SPS into LHC and circulated for several hours, and the lifetime of this system was determined to be more than 40 hours. So this is really possible. This is a very big step in the right direction towards gamma factory. So yes, this is your 4 gamma square energy boost, and so you can access, depending on the gamma and initial photon energy, a very broad range of energies of the secondary photons. I guess I already explained this. And this is the part about the cross sections. So it's a very big boost in the cross section and the available fluxes. So now, suppose you build such a light source. What can you do with this? And I think personally that this is only limited by your imagination, and we keep discussing various exciting things with different people, and in particular we are almost finished compiling the first, in which I hope will be a series of papers. This is called Atomic Physics Studies at the Gamma Factory, and this is spearheaded by Andrei Suzhikov from PTB, and so this basically catalogs what kind of atomic physics you can do, and I'll tell you briefly about it. So to get the terminology straight, it depends a little bit of what community you are talking to. If you're talking to accelerator people, they call these ions PSI, partially stripped ions, because they are used to work with fully stripped ions. And if you talk to atomic physicists, they like to call them highly charged ions, because they typically work with only a few electrons stripped, so they go from another direction. But it's really the same thing. And if you, for instance, start thinking about hydrogen-like ions, so basically a big nucleus and just one electron, then in principle it's a very simple system. It's just like a hydrogen atom, and you just need to put the proper powers of Z. Z is the atomic number, right? The charge of the nucleus, and sort of see how things scale. For instance, the energy scales as Z squared, the fine structures splitting as Z to the fourth. Then there is hyperfine splitting goes as Z cubed, Lamb shift as Z fourth, and so on and so forth. There are some interesting scalings. And one interesting thing is that, of course, it brings you to, Eric might be interested in this number, it brings you into the strong field regime. For example, the electric field at the lead nucleus could be something like 10 to the 16 volt per centimeter, and so you can start studying sort of this high field QED things. And there's a lot that's being discussed. So just a few months ago, the Gamma Factory group has submitted a proposal for sort of a full-scale proof of principle experiment that was going to be at the SPS, not LHC, and this will use, for technical reason, lithium-like lead, and there are some parameters here. I should tell you that this whole Gamma Factory group is part of a very exciting initiative at CERN, which is called Physics Beyond Colliders. And this is basically a program that was initiated by Fabiola Gianotti and a group of enthusiasts to make sure that CERN, this wonderful European laboratory, survives as a relevant physics center into the future, where, as we heard in Dima's talk, accelerators are very expensive and very few of them are going to be built in the future. So CERN decided to look what can it do, which is very good physics, but beyond the collider concept. And this fits because it is with LHC, but it's not in the collider mode, okay? Or I guess you can say that you're colliding with photons. Yeah, I don't know. Anyway, there's a lot of atomic physics, which maybe I'm going to skip for now, not to get you bored. But I would like to tell you about maybe one example of fundamental physics, and in fact, it's an example dear to my heart, and this is how I got involved myself in this Gamma Factory business. It goes back to 97, actually, a long time ago, when with Max Zolotaryov we published a proposal for measuring atomic parity violation in basically this Gamma Factory configuration. We didn't call it Gamma Factory, but the rest of the components were there. And so when people started thinking about the gamma factory, they called me up and said, join us, and I gladly did. And the idea was that we wanted to look basically at hydrogen-like transition, 1s, 2s, with the motivation for this thing for measuring parity violation in hydrogen, that the atomic theory is very easy to do, and so you can extract the weak interaction parameters precisely. And just to remind you that you have these 2s and 2p states that are close to each other, and the weak interaction provides mixing between 2s and 2p, which is inversely proportional to the energy denominator between these two states. Now, when we were thinking about it, there were several rings we were considering. There was a relativistic ion collider at Brookhaven, and actually SPS and LHC. So this shows you the time scale with which anything related to accelerators is developing. This was in '97, and it's actually up to date, so more or less. Right, and yeah, right. And then we looked again. This is again the Z scaling, basically, and because it's hydrogen, the nice thing is you can write all the formula analytically, or almost everything analytically, and you see these different scalings of things. Yeah, so we also proposed to use exactly the relativistic Doppler tuning. This is the now the resonant condition. This is Z squared from the scaling of the energy, and 10.2 is from the hydrogen, and we need to make it 2 gamma times the energy of the photon in the lab frame. So you can see that with LHC you can use atoms as heavy as 48. So this is cadmium, for instance. Now, not only hydrogen-like systems are interesting. So remember the Bouchia law for. So you want to use heavy atoms because there is a fast enhancement of parity violation due to large nucleus. It's actually even Z to the 5 for hydrogenic ions, not Z cubed like for neutral atoms. So it's even faster. And then you also want a small energy denominator between the mixing states. Okay, and so it turns out that there are sort of level crossings as a function of the number, the nuclear charge for different systems, and so you can use these and enhance parity violation effects. So these are of interest. Okay, so parity violation is one interesting thing that you can do, but you can also do other things. For instance, we think that if you shine not normal photons, so to say, but twisted photons onto your relativistic ions, we believe that these high energy gammas, the secondary gammas, are also going to be twisted. Now, I don't know if you know what twisted light is, but basically the idea is that you don't know. Okay, good. The idea is that a photon has a spin, right? And it's a spin 1, but there are two possible projections on the on the direction of propagation, right? It's +1 and -1. But this is spin, and the question is, can there be an orbital angular momentum? And the question is yes, there can be an orbital angular momentum, and in order to have such a thing, you need to prepare a somewhat special configuration of this. This turns out to be a donut beam where to avoid the singularity in the center on the axis, the intensity has to go to 0 there, but you can easily arrange sort of a phase distribution shown here, and you can actually have also orbital angular momenta, and people have generated up to fairly high orbital angular momenta. And so again, if you have a donut beam and you basically measure the relative phase of the photon as you go around, it just can be 2 pi n, and this corresponds to this orbital angular momentum. And people use these things for various interesting applications, and we can make, we believe, the gamma rays having this property as well. And this book actually has some elementary description of this twisted light. It's become a very, very popular thing in recent years in optics. A lot of people. It's they are very easy to generate such beams. Right. So I guess I would like to summarize and also maybe tell you a couple more things while I'm summarizing this about some other applications beyond atomic physics. So in the gamma factory, you have already interesting spectroscopy which you can do in the Lorentz boosted primary beam. Okay, so just which ions do you excite? You can do the spectroscopy of those ions. But then when you produce the secondary beam, then you have a much higher energy photon beam which you can use. So you can do the spectroscopy of partially stripped ions. You can do fundamental symmetry tests like the parity violation measurements that I just described. And you can actually measure various things like neutron distributions in the ions. And now you can think about measuring parity violation. We already discussed, like in the terbium atoms, we measure parity violation in a chain of isotopes, different isotopes. We are planning to do a measurement on different hyperfine components to measure the nuclear anapole moment. But here we can measure in a chain of ions with different ionization stage. And if we do that, then we can probably figure out a lot of atomic systematics very well. Now, there's another thing we can do. I mentioned optical pumping many times. So it's very easy to take the angular momentum of the photon and transfer it to the atom, including these partially stripped ions. And now you can have polarized beams, and you can use them for polarized ion scattering for fundamental physics. You can do beam dump experiments. That's one of the ways people are looking for axions and other exotic particles, and the idea is fairly simple, but there is a large community that is doing this kind of experiment. You take a high energy beam and you shine it into a pile of dirt, so the beam is absorbed, and then you put your detector on the other side, and then you see what happens. And if an axion is involved or something like this that interacts weakly, it can travel long distances, and a lot of people do this. So now you can have a beam of photons with well-controlled polarization. And actually, I don't think that people have seriously looked at advantages for beam dump experiments for this high energy, and this is an open question whether there are any interesting twists that one can have here. So now, why do people in general accelerate relativistic ions? Well, they collide them and they study things like quark gluon plasma. Now, if you have some imagination, you can think that you can polarize the ions going right and ions going left before they collide, and now you can have polarized heavy ion collisions. And we think that it's very interesting. We just need to convince people who do this kind of quark gluon plasma that is actually an interesting thing. I'm personally convinced this is super interesting, but this is work in progress. And as I already mentioned, you can make these twisted light beams or vortex beams, X-rays and gamma rays, and do photon scattering experiments. And I must say, I'm so enthused about this gamma factory that I even went so far as to design a bumper sticker. You know, in the U.S., you drive around, you put things on a bumper sticker, and this is my bumper sticker for gamma factory. And this happens to be actually the official emblem that I incorporated of the gamma factory. Right. So we are approaching the end. I just have 5 minutes left, and so I'd like to bring it back to Galileo here. Yes, of course.
So I'm thinking about what's happening in these ions, right? So at least in the lab frame, they've absorbed a photon and they're going to start emitting photons. And then in the ion frame, they emit it in 4 pi. But then in the lab frame, they emit it in 2 cones, one up the back, one up the front.
No.
Because of relativistic beaming, yes?
No, only front.
Where's the...
It's well, if it's emitted directly in the back, I guess it will still go in the back, but it would be shifted down.
Right, that's what I'm thinking about. So if you have the one up the back, that's going to be Doppler shifted back the other direction.
Yeah.
And then you have one
But there's no cone, so most of the intensity will go. If it's emitted just at a tiny angle, the relativistic transformation will collapse that angle into 1 over gamma. It's true that if you measure the spectrum across this 1 over gamma, you would have the highest energy in the center, and then it would be falling off. So if you're worried about highly monochromatic beam, you would need to spatially filter it. That's true. Mm-hmm.
Why wouldn't you have cone going to the back as well as front? It's relativistic. You could collimate that way, or could collimate the other way.
No, because let's draw some angles and relativistic transformation of transverse and longitudinal component.
I think it's probably some point where we thought about the star moving relativistically and where the light beam is. And I think you get both out the back and the front for that, right? I might be remembering wrong.
No, I don't think so. But let's not waste time here. Yes, Eric.
Very strict deadline of 4 today. Somehow coming up with
I will shut up in 3 minutes. Yeah. So how to do Galileo to me is the biggest hero of science of all times, because he's the founder of experimental science. And his method was, make a new tool. In this case, it was a telescope. It was not the first telescope, but it was certainly the best telescope, and it allowed him to discover a lot of things, starting with moons of Jupiter and so on. So the prescription is you build new instruments and devise new techniques, and then you have good ideas, and then you have to have discoveries that you gotta have them. And I think that gamma factory is an example of potentially a new tool, and I'm sure it's going to lead to discovery. Now, for the ideas, I had some suggestions today, but I hope that people in the audience will contribute to the ideas of what you can do with this new tool. So the other things to remind you, so I talked a lot about couch experiments, and a lot of these couch experiments they rely on availability of nice data. And so a few years back, Andrei Derivenko and I, we wrote a little, call to action, a pamphlet called a Data Archive for Storage, for storing precision measurements. So a lot of you can do your couch experiments whenever you have an idea.
Community, we call it recasting.
Yeah, recasting. And And then we talked, actually the theme, but I guess I was invited here to talk about precision physics with atoms and molecules, and I remind you that there's a review paper. I'm very happy to say that it's only a couple years old, and it's completely outdated now, but still you can use it as a starting point. It's not completely outdated. And by the way, this is Mariana Safronova, the first author here, and there are some other people I'd like to point out to you. For example, this is Alexander Sushkov, who was a graduate student, and he's now a professor at Boston University, and he leads the Caspar Electric effort. This is Professor Erwin Hahn, who discovered or invented everything in NMR, including J coupling that I showed you today. This is Professor Pustelny, whom you might remember from our Grill the Professor session, that the person who explained things to his students 3 times. Yeah. He was a graduate student as well. Anyway, another good people here. We started by some general remarks about non-collider physics, and if you are interested, they are written up in this European review thing, and a lot of anecdotes are collected there as well, if you care. I love Physics Beyond Colliders program at CERN, and I'm extremely grateful to the people who have initiated it. And I also would like to end with advertising one of our books in a shameless way, and you can read it in English, also in Russian, which is not shown here, and in Japanese since last year. And so this is the very last thing before the deadline, and this is what we did, and we covered everything, and I really thank you for your attention, and that's it.
Thank you so much for these lectures. So we have to get out of this room quickly.
Evacuate.